So this is our fourth review video for the final exam. This one is all about equilibrium, not only at a point with just ropes, but also on a beam. And we've got kind of two different styles of questions that you could see. You might see a whole bunch of ropes just simply knotted together. Then in that case, all you can do is just balance forces. Equations in that situation might be, oh, hey, the forces that go to the left balance out with forces that go to the right. They add up to 0. And not only that, the forces that go up balance out with forces that go down. The ups minus the downs are equal to 0. Some interesting techniques to try to pull that off nicely. You might be able to do one big triangle. Just add up all your forces in a picture. As long as there are only 3 of them, that works really well. If you've got a beam, I'm just going to jokingly call them sticks. If you've got a stick, then not only can you balance forces, but you also have the option of balancing torques. So equations for balancing torques, we're going to have that the torque counterclockwise balances out with the torque clockwise. And when you go to find any given torque, it's going to be an R multiplied by an F multiplied by the sine of the angle in between the R and the F. Some interesting techniques for that speed things along. Definitely consider putting your pivot when you go to decide where you're going to be working with your torques. Try to pivot at an unknown force. It makes the math very, very nice. You don't have to, it works everywhere, but the math is really nice if you pivot at an unknown force. So let's jump right into it. Let's try this thing out. I've just got a whole bunch of old provincial exam questions and we'll give each one a try. So this one here, there's a 6-meter long uniform beam. Okay, right away I know how I'm going to be doing this one. This one seems to be some sort of question about beams or sticks. I'm going to be thinking about where do I put the pivot in order to get this to work. It's 25 kilograms, it's suspended by a cable, and an 85 kilogram object is hanging from the end. Okay, great. And you're supposed to try to find out how tight the cable is. Well, I would start doing my free body diagram, maybe right on the picture. There's going to be a nice impressive mg going down here. The beam itself has some mass, and I can pretend that its mass is all right in the middle. It said it was uniform. So if it's 6 meters, then 3 meters along, I can put all of the mass of the beam right there. There's going to be a tension from this cable. In fact, you're trying to figure out how tight that cable is. And there is another force, or maybe even 2, depending on how you want to count. There's going to be this force from the wall. It's going to be doing something kind of strange here. I really don't know what's going to be happening there. It's kind of got like a left and right and an up and down happening at the same time. And so that's really confusing. And that kind of motivates me to put my pivot right there. So when I go to do my torque calculations, I get to ignore that crazy force if I put my pivot there. And I'm going to jump right into doing pivots. I'm going to say, hey, you know what? The torque's counterclockwise, have to balance out with the torque's clockwise. I like taking my pencil and just like lying it right down on top of the beam there and saying, okay, if I pinch it where that pivot is that I've drawn in green, then what is trying to take that pivot, that pencil, that beam, and rotate it counterclockwise? And that would be the tension. And now I just get into a rhythm, into a cadence for finding these torques. It's always R, F, sine of the angle. So the R, how many meters is it from that green pivot to where the tension touches? Well, that's 4. How big is the force? Well, that's tension. What's the angle between the beam and that force? 67. So sine of 67 degrees. And that's it for counterclockwise twists. Then I go to the other side of the equation. Clockwise twists, I've got a couple of mg's. One of them is the beam itself, and it's again just a rhythm, R, F, sine of the angle. The R is 3. The F, it's a 25 kilogram beam. 25 by itself is not an F, it's an M. But if I multiply that by the gravity field strength, there, that is an F. And then the angle. Well, I'm just going to erase this crazy force that I don't like. If there's a 75 degree angle near the wall, then just kind of thinking about Z shapes, there's going to be a 75-degree angle where that mg meets up with the beam. So I'm going to go with 75 degrees there. But there's another clockwise twist. At the end, 6 meters from the pivot, I have a force that's 85 times 9.8. And again, a 75-degree angle. There's only one thing missing there, it's the tension. I have to be totally honest, I don't even know what the answer is, and I don't care. We shouldn't care about what the answer is right now. We're just trying to get comfortable with the ideas. And the idea is if you've got a beam, if you've got some sort of stick, then you can go with torques. And if you put the pivot at an unknown force, which I did, there was some weird force coming out of that wall right there, then you get to ignore that force, and all you have to do is work with all the other ones, and you go RF, sine of the angle, every single time. The second example, I put this one on the review very deliberately. So many times we were always pivoting at the very end of your beam, at the end of the stick. And it's not because it's the end that we do that, it's because that's where there was an unknown force. And so this one kind of stops us from doing that. There's a 25 kilogram droid there. And it's a 5-meter long shelf. Great, got some dimensions all on there. And the shelf itself is 12 kilograms. And you have to find the tension in each cable. Here's what I would do. Start off with your free body diagram. We have got some sort of tension here. I'm going to call that tension 1. There's another rope. I suspect it's a little smaller because it's farther from the droid. Tension 2. And a couple of downward mg's. The droid is going to be applying a force here. I'm going to call that, that's a strange looking M. I'm going to call that capital mg because it's a little bit bigger mass, it's 25 kilograms, than the actual beam, the mg here. Okay, I've got all my forces on there. It's definitely a stick question, so I'm going to jump right into doing torques. And what I want to do now is put the pivot at an unknown force. I know the mg's, but I don't know the tensions. Don't put your pivot at the very end of the stick. Pick one of the tensions. So that's what I'm going to do. I'm going to pivot right here. Say, okay, what would be causing the stick to twist counterclockwise? What would be causing it to twist clockwise? And I want to make sure I get a nice little balance going for those. So here goes. Torques counterclockwise. Balance out with torques clockwise. Okay, I kind of lie my pencil down on the paper right on top of the shelf, pinch it where the green pivot is, kind of let it wiggle around, and counterclockwise it looks like it's tension 2. So I just start doing RF, side of the angle. The R is how far is it from the pivot to that force? Well, that's 3.8 meters. So I would have a 3.8. Then the F, well that would be T2, and then the angle. Sine of 90 degrees. Kind of wasting my time there, really. Sine of 90 is 1. Now, clockwise twists. There's the droid. It's 0.8 meters away. So 0.8 for the R. The F. I can't just say 25, but I can go 25 times 9.8. And, you know, officially you're supposed to go sine of 90. Whatever. You're wasting your time. It's 1. There's another one. There's the little mg. Now, if you're looking at this going, well, wait a minute though, wouldn't there be a little bit of this shelf trying to twist it counterclockwise, that part there? You don't have to worry about that. If you found the center of mass, which we did right here, you can pretend all of the mass is there, everything works out nicely in the math, and we can say that that center of mass, it's going to be, well, it's half this 3.8 number, so it's 1.9 meters away from that nice green pivot. So you can say its R is 1.9, and you can put all of the mass there, all 12 kilograms, times your 9.8. And if you can fit the sine of 90 in there, you go ahead and put it in there. It's 1 anyways. It doesn't make any difference. This is going to let you find this value for T2. You'll have that number, and you're halfway done the problem. But now we should find T1. You can start all over again and put your pivot at the other rope. But a nice way to do this, to finish it off, would be to say, well, wait a minute. The force is up. Have to balance out with the forces down. The ups minus the downs are equal to 0. So tension 1 plus tension 2, and you can take your answer from the first part and put it in here. That has to equal 25 times 9.8. plus 12 times 9.8. There are no r's when you're doing that force equation. No r's at all. And then you can find what T1 is, and you're done. So, key things. When you're doing torques, get in that rhythm of RF, sine of the angle, and always put your pivot at an unknown force. Third question here. Got a shelf, it's 3 kilograms. The whole thing is 1/2 meter wide, and it's supported by a bracket. And the diagram didn't have it drawn in here, but I'm going to assume that there's like a little pin here as well, so that this bracket can only like push or pull, just like a rope can pull. Well, a bracket can push and pull straight on. So there's going to be a force from this bracket that lines up with the bracket. So I'm going to suggest to you that that force would go this way on the shelf. I'm going to call it FB for a bracket force. Other forces acting on that shelf, well, right in the middle, I can pretend all of the mass of it is here. There's going to be an mg going down. And back at the wall, there is some crazy, scary, complicated force going on there. It's probably pulling back towards the right. Whether it's up or down, I don't even know, but it's going to probably be doing something weird over here. That is sufficiently bothersome that I'm going to deal with this one using torques, and I'm going to say, you know what, why don't we pivot right there? Because if we pivot there, we don't even have to worry about that crazy force. We're ready to go. Okay, so we're going to do torques in order to figure out exactly how much force that bracket exerts on the shelf. We're looking for FB. When we go to do torques, we're going to do R's and F's and sines of the angle. I'm just going to help you out here with those angles a little bit. The angle, 50 degrees, kind of makes an X shape, and that means that there would be a 50-degree angle here also. Because of angles on a line, this angle out here would be 130 degrees. And if you're wondering, well, which one should I use? Which one is the angle between the beam and the force? You can use either one, and it makes no difference whatsoever. So I'm jumping into torques. Torque counterclockwise is equal to torque clockwise. Put your pencil down on top of the shelf, pinch it right where the green pivot is, kind of waggle it, and ask yourself, who's trying to make it go counterclockwise? And the answer to that is the shelf itself. So if it's a 0.5 meter long shelf, the mg is halfway along. That would be at 0.25 meters. Then there's the force. Well, it's a 3 kilogram shelf, but you'd have to multiply by 9.8 in order to get a force value. And then the angle. Well, that mg meets the shelf at 90 degrees, so sine of 90. Clockwise, you've got the bracket force. It is located 0.2 meters away. That's the R. The F is what you're looking for. And then here, you've got your sine of your angle. You could go with 50 degrees, or if you wish, you're not going to hurt anything, you could also go with 130 degrees. Nope, nobody cares. It's a reference angle thing. It's not going to make any difference whatsoever. I got to be honest, I don't know the answer. Don't care at all, actually, because we're not worried about this particular question. We're worried about just the ideas in general. If you've got a beam like this shelf, think about using torques. Think about putting a pivot at an unknown force like that. That way you get to ignore it. Works really well. The next question is not a beam. There's a big long roof, and then there's this floodlight that's hanging down with a couple of ropes. And you're asked to find the tension in the left cable and the mass of the floodlight. No torques to worry about here, just forces. And they're all working together right here at this point, at that knot. So I'm just going to get my diagram ready to go here. I've got one force over here, another one going back kind of to the left along those ropes. I don't know which one is bigger. Maybe I'll call this F1. Maybe this one could be F2. And then gravity is going to help us out with another force. It's going to do an mg for your floodlight going down like that. This is nothing but one big knot of ropes. There's no beam. So no torques. We're just going to go with the idea of adding the forces up. Lefts equal rights and ups equal downs. But the good news, there are only 3 forces. Go with the big triangle. It's a really nice way to get this question to work. Now, when I go to do my big triangle for these kind of solutions, I always draw the nicest forces first. And mg looks pretty clean to me. So I'm going to draw the mg going down like that. Say, okay, beautifully lined up with my paper. That one is mg. Now, the one that you draw next is entirely up to you. You could draw F1 next or F2 next. You don't have to draw them in any order. So I'm going to go out of order. I'm going to draw F2 next. It kind of goes this way. And then F1 goes back to the left and up, like that. They all add up to nothing. And our job is going to be to see if we can figure out how big F1 is. We know that F2 is 140. We were given that. We're looking for F1, and well, we're kind of looking for the mg as well, the weight, but we'll use the weight to find mass. Now, angles. Be careful with this. It's not super hard, but it's something you got to watch out for. This 40 degrees, that is an angle between F1 and something that is flat. So go down to your picture, and where you find F1, if there isn't anything that's flat, you got to go add something that's flat. That way you can get it into your picture. So we've got a 40-degree angle here and a 40-degree angle there. And if that's 40, then I guess this one between the two forces is a 50. Same thing with the other force. Take a look and see where it's actually referenced to. It's referenced to things that are flat. So I want to go and take force 2 and say, okay, compared to things that are flat, I'm going to add them in if I have to. That is a 60. That is a 60, and I guess this, being in a corner, has to be 30. Take the extra couple seconds to just say that to yourself. Okay, these angles are compared to things that are flat. And now it's really quick. You want to try to find out the tension in that left cable, the tension in what we've called cable number 1. You can just do sine law. You've got this beautiful working pair. You've got this 50-degree angle and this 140 newtons. We can use that with the sine law. We can go sine of 50 is equal to, or sine of 50 divided by 140 is equal to, hey, you want the left cable? The left cable looks like it's opposite a 30-degree angle. So sine of 30 degrees all on top of F1. A little cross multiplying and you're done. I don't even know what the answer is, but you can easily do that and find out what the value is. You can do the same thing again to work on the mass of the floodlight. Working pair, sine of 50 on top of 140 is equal to, okay, the mg, well, you got a 40 and a 60 there. It looks like 100 degrees. So sine of 100 degrees all over, okay, one minor little thing, it would be all over the weight. Right? mg is weight. It's a force of gravity. So sine law and the idea of balancing forces out, it's going to give you the weight. You got to then go and say, all right, hey, I can divide by g and I can find out how big m is. Right? That's not that big of a deal. So for that one, no r's. Just working with forces, going with a triangle. I'm going to do the same thing with question number 5, the second to last one. For question number 5, I don't see any beams there. I just see a whole bunch of things all kind of tied together, and they're going to be applying forces right here at that knot where things are all tied. And so as far as free body diagrams go, yeah, I got a force this way, got a force that way, and I've got an mg going down. Maybe I'll call this one F1, this one can be F2, and then an mg. This one's even nicer than the last one because you've got two nice forces in there, the mg and the F1. And it does not matter which one you draw first. I'm going mg. So I've got mg, then I've got an F1, and then pulling back up and to the right, I've got an F2. By the way, just looking at this picture, without any numbers, I can tell you that F2 is bigger than F1. It's a hypotenuse, right? But we have some angles, 60 degrees on F2, and things that are flat. Okay, so I'm going to my picture, F2, things that are flat. Well, that's down here. This is 60 degrees. Add something that's flat. That's a 60. That's a 30. And lucky us, a nice beautiful right angle in there. You don't even have to do the sine law with this one. You can do SOHCAHTOA and it'll be great. 0.5 kilograms. So it looks like the mg on this one, if we go 0.5 times 9.8, we've got 4.9 newtons going on there. You're trying to figure out how tight that horizontal string is. That's F1. You could do this. It'd be this simple. You could just do SOHCAHTOA. You could say tan of 60 degrees would be the opposite, the 4.9 divided by the F1. Swing that around and you're done. I don't even know what the answer is, but it takes like 10 seconds and you're there. More important than the answer, no R's, no torques, just forces all adding up on a knot, adding up to nothing. Only 3 of them, so we were lucky. We just went with a triangle. Last one. Okay, there's a beam. So as soon as I see that, I know I'm going to possibly use some torques. It looks like there's going to be some pretty crazy angles going on in here. But that's okay. I can still get into that rhythm of RF, sine of the angle. So uniform 2.4 meter long beam, great. Got how long it is there. It's 3 kilograms. It's hinged at the top, held in place by a cord, and there's a mass. Okay, so yeah, I know there's a mass with a rope, but it's really just a big torque question. So forces. The forces are going to create some torques. I've got an mg going down here. There's this cord that's pulling off that way. So I'm going to call that, I don't know, maybe I'll call that T for tension. The beam itself has a mass, so I'm going to put its weight right in its middle, right there, pointing straight down. And there's one more force, and it's weird looking. It's acting at the top right end of the beam. It's holding it up and pulling it to the right. It's doing some weird, crazy thing like this. It kind of bothers me a bit. That is why I'm going to pivot there. Because there's an unknown force, and it's actually got 2 components that I don't know, left and right and up and down. So I'm definitely going to pivot there. So if I'm going to do torques, I have to start thinking about angles between the beam and those forces. So I got to do whatever it takes in order to find those angles. And it might be things like this. You know, maybe I'll take this 35 and maybe make like a Z shape like this and say, okay, that's 35. Making a little Z shape in there. And then there's also another 90 degrees in here. So all in all, this whole angle, I guess the entire angle there is 125 degrees. And if that's 125, so is this one. This one's also 125. Oh, what else can we do? Oh, you know, you could do another Z shape. I'm going to make a real mess of this picture here for a minute just so you can see it. And then I'll erase it. There's a Z shape that goes kind of like this. And I'm going to put the 35 down in this bottom corner. I think that'll help me figure out what's going on with that tension down there. Okay, so adding a little line in, that's 35, and then angles on a line, that angle there adds up with the 35 to make a straight line, so that looks like 145 to me. This is not the only way to come up with those angles, but I think I'm okay. I've got a 145 degree angle on the tension and a couple of 125 degree angles. It's a beam, so I'm going right on into torques counterclockwise equal torques clockwise. Counterclockwise, take your pencil, lie it down on the paper, pinch it right where the green pivot is, let it wobble around a bit. Counterclockwise, it's going to be those mg's. So here we go, we're going to go R's and F's and sines of angles. One of them is the little mg that's actually for the beam itself. It's a 2.4 meter long beam entirely, so the center of that mass is 1.2 meters along. It has a mass of 3. That's not a force, but if I multiply it by 9.8, I'm fine. And then the angle between the beam and the force, that's all that we care about is what's the angle between the beam and the force, not between the beam and the world, but the beam and the force. That angle is 125. But there's another one kind of like that. It's the big 5 kilogram exerting some weight. You have to measure from the pivot to where that force is acting. So I'm going to use the overall length of 2.4, and then that little end part that hangs past of 0.5, I'm going to subtract and say, hey, just by subtracting, there's 1.9 meters of beam between the green pivot and that 5 kilogram rope. Okay, the force, 5 kilograms times 9.8, and again, a sine of 125. Going the other way, going clockwise, all the way at the end of the beam, 2.4 meters to the end. There is a tension, and I also have to have the sine of the angle, sine of 145. Okay, yeah, it's big and it's messy looking, but there's only one thing missing. You just slosh everything around and you come up with the answer. I don't actually have that answer, don't really care. It was the setup that made more sense to me to worry about. So it's a beam thinking about doing torques, and I know that I can ignore a force if I pivot there, and that's why I did that. That force was really confusing, so pivoting there I got to ignore it. If there is no beam, then you can't do torques, then you're just balancing forces and you hope for one big triangle. And that's the end of the 4th video.